Hello, I'm CFD support engineer, and in this video I will show you how to set TCFD pump tutorial from scratch. First thing I need to do is I need to specify a setup file. I go to Save As, go to Desktop, to directory Radial Pump, where I have my STL files, and in the directory next to STL files I specify the name of my new TCFD file. I name it pump.tcfd. I press OK. And now the path to my new TCFD file appears. Then I need to change simulation type. I already mentioned that I want to simulate radial pump, and that's why I select pump. This is everything to section general. So I press apply and continue to section physics. In section physics I have multiple subsections. First is time management. In time management I decide if I want to compute steady state or steady state plus transient simulation. In this case I'm computing only steady state simulation. Then there are speed lines. Speed lines allow me to compute multiple rotation speeds in one computation. So if I use more speed lines, I will have more rotation speeds in rotation reference frame. And one speed line will be computed with one rotation and another with different one. And I will be able to set different boundary conditions for different rotation. In this case, I will compute with only one rotation speed, so one speed line. But I want to compute 3 points. 3 points mean that I will have 3 different boundary conditions. Then I need to specify point iteration, and because this is TCFD tutorial and I already know the results, I know that 500 iteration is enough for case to converge. But if you did not compute your case previously and you're starting it from scratch, then I recommend you to use more iteration, even couple of thousand iterations, to be sure that your case converges. And later on, if you recompute it and you know how much iterations you need, then you can lower or increase the number of iterations. If you have very large number of iterations, but the case converges much faster, then it can stop because of convergence check, which I will show in later section. Also, this case is incompressible, and if I computed compressible case, it always needs more iteration. So good starting point for incompressible simulation is like 1000 to 3000 iterations, and for compressible case I recommend much more, like 4000 to 7000 iterations per 1 point. This is everything to time management, and I can continue to fluid properties. In fluid properties I can set gravitational acceleration, but in Turbomachinery we can neglect it. Then physical model for pump and water is always incompressible, so I'm not able to change it. Fluid name is water, and I will use fluid defaults. Besides this, I'm able to change the reference pressure, but I can leave it at 1 atmosphere. Then there is cavitation risk or multi-phase cavitation for transient simulation, and additional parameters if I want to compute h, or I can add passive scalars to my tutorial. But in this case, I don't want to. So I can continue to turbulence. In turbulence, I will use standard k omega SST model, and here I don't need to change anything. On the walls, I will use standard wall function. I can close turbulence and continue to rotation reference frames. In rotation reference frames, I set rotation to my parts of geometry. The first frame is always static, so I have an option to have part of geometry which is not rotating. Second default reference frame is rotating. Here I need to specify the correct axis of rotation and also correct origin of rotation. Then when I checked rotating, I'm able to set rotation speeds. I know that the pump is rotating with 1770 RPM. So I change it to RPM. This multiple reference frames allow me to compute cases with multiple rotors, and which we will have different rotation speeds and also different axes and origins of rotation. For more information about case like that, you can check tutorial double rotor axial fan, where we set two different rotors with different axes and origins. I can close rotation reference frames, close physics, press apply. To be safe, I can save the changes, and I can continue to components and mesh. First, there are components. Section components is a very important part of TCFD setup, because here we decide what will be meshed and how it will be meshed. First line here is scale factor. Scale factor allows us to rescale the geometry if it is in different units than meters. My geometry is in millimeters, so I need to rescale it. And that's why I change units to millimeters. Then there are number of components. I know that my case have three components: inlet pipe, which is static, impeller, which is rotating, and volute, which is static component. That's why I change number of components to 3. Now I have tab for every component, and I need to set every component separately. For the first component, the first line is geometry source. In this case, I will be looking for directory with STL files, because I have STL files of my geometry, and I will be meshing it with Snappy Hex Mesh. I also can have different options with external meshes from OpenFOAM or different softwares. But in this case I have STL files, and that's why I need to specify STL directory. It's the directory where I have my STL files. I click on 3 dots and go to the directory where I have my STL files. I know they are on desktop, in directory radial pump, STLs, next to my TCFD file. I clicked on STL and press OK. Now the directory is specified, and all STL files from this directory are loaded into patches table. Then I can rename the component. I know that the first component is pipe, so I name it pipe. Then, as I said previously, this component is static, it's not rotating, so reference frame stays static. It's also full geometry and no periodic segment, so I leave number at 1. And then there is patches table. Before I continue to patches table, I press apply to apply the changes. Now, in this table, I specify which STLs should be used for mesh generation of the first component pipe. There are 3 STLs for pipe: inlet pipe inlet, inlet pipe outlet, and inlet pipe wall. I'm going to use them by double-clicking on type and changing type not used. In this case, after double-click, I can choose from my options, and I know that inlet pipe inlet is inlet into my whole geometry. So it's inlet. I select it. And now when I clicked outside of this line or outside of table, inlet pipe inlet turns green, and I know that this STL will be used for pipe meshing. Then there is inlet pipe outlet. Inlet pipe outlet is not outlet of my overall geometry, so I cannot use outlet, but pipe is connected to impeller. Impeller will be second component, and this means that inlet pipe outlet is outlet interface between first and second component. So I select outlet interface, click to next line or previous line, outlet turns green. Now, because it is interface, I need to connect it to second component, because otherwise program doesn't know which interface is connected to which one. So now I click on the mouse, right mouse button, and connect outlet of pipe into component 2, which will be impeller. And the last STL is wall. So I select wall. Now I have all STLs, and reference frame stays static in this case. I also don't need to change the minimum and maximum refinement levels, because pipe has very simple geometry and these default values are okay. Then I'm not going to use boundary layers, and I'm going to use 0 mixing planes for this interface between inlet pipe and impeller. 0 mixing planes refer to frozen rotor interface. This is everything to patches table. Now I'm pressing apply to apply the changes, and if I want to see the geometry, I need to click on an eye next to components to make it visible. I clicked, some random warning appears, but it's not important. I can clear it, and now I can see the STLs of my pipe. I continue. Next, there's gap refinement, but this is advanced setting and I'm not going to use it in this case, so I skip it. I also do not want to use cylindrical mesh. What I want to set is background mesh size. This is very important parameter because it describes how fine the mesh will be in the mesh volume. To help me with the selection of this parameter, I click on Show Background Mesh Wireframe. Now the axes appear, so I have a brief notice what are dimensions of my case, and now I'm going to select some size of my background mesh cell, which is cell in mesh volume. I will start with 20 millimeters in each direction. And when I click outside, the background mesh size appear. The background mesh size shows me the size of cell in the mesh volume. 20 millimeters are large, and I want to refine it better because I don't like an idea of having only a couple of cells in my mesh volume. So I decrease it to 10 in every direction. The background mesh size wireframe changes also, and now this wireframe is finer, and this might be valid value for my background mesh size in pipe, because pipe is very simple geometry, and also on the wall and outlet interface it will be refined once, so size of the cell on the wall and outlet interface will be halved with respect to background mesh size. So I have my background mesh size, I can hide the wireframe, and I can continue to internal point. I again want to show internal point to make it easier to select it, and now I want to put it inside. To make it easier, I decrease the opacity of my geometry. I go lower and decrease the opacity. Now I'm able to see inside of my pipe. Internal point is at 0, 0, 0 at the moment, and I want to put it inside. So I left click with the mouse and I drag it inside. Now when I rotate the geometry, I see that my internal point is inside. By selecting internal point inside, I'm telling the program to mesh it from internal part. So the internal part of the pipe will be meshed. If I selected it outside, I would mesh the pipe external part. This is useful for external cases, external aerodynamics cases. So my internal point is correct, I can hide it, and now I continue. I do not want to add any refinement regions in this case, and I also do not want to add boundary layers in this case. I can continue to component graph, where I can get an idea in which state my mesh generation or mesh setup is. So I specified inlet. I have my first component named pipe, which is static. As inlet, I have inlet pipe inlet STL, and there's outlet interface. This outlet interface should be connected to second component, but the interface or the arrow between these components is only dashed because it's connected from one side. I connected the interface from first component with second component, but for this connection to be complete, I also need to connect interface from second component to the first component. Then the line will be thick and the connection will be complete. To do it, I have to go to second component. This is everything for the first component, so I press apply and continue to second component. Component 2 has independent setup with its own geometry source. So if I wanted to use external mesh, I could use it for this component, but I will stick to STL files. And that's why I need to again specify STL directory. I'm already in radial pump STL, so I only press OK. Second component name is impeller. Reference frame in this case is rotating, because impeller is rotating. No periodic segments. And now I specify the correct impeller patches or STL files from patches table. I again double click on type and impeller blades is type blade. Then there is hub, which is hub. Impeller inlet is inlet interface, because impeller inlet is the same as inlet pipe outlet. So I choose inlet interface, right click with mouse and connect it to pipe. Then there is the impeller outlet, which is outlet interface. Impeller outlet is the same as volute inlet. So in this case, outlet interface, right click, and I need to connect it to third component, which will be volute. And the last impeller patch is shroud. So I have every patch specified, and now I need to choose better details. I know that the reference frame is rotating, but I also have an option to select if some patches are rotating or not rotating. And that's why I need to change reference frame to rotating, because blades are rotating. In my case, hub is rotating and shroud is rotating. Then there are refinement levels on walls. In this case, I need to change these values because I have more complex geometry. I press apply to see it. So here I see the geometry of impeller. And if I rotate it a bit, I see that distance between blade trailing edge and impeller outlet is small, and that's why I will need to refine geometry in that area. I know that my tutorial uses values of minimum and maximum refinement levels on blade to 3.3. On the hub it's 2.2, and on shroud it's 2.2 also. This means that refinement is always with respect to background mesh size, and values 1.1 mean that on these patches the mesh is halved once with respect to background mesh size. On these patches it's halved twice, and on blades is halved 3 times. So the cell is 8 times smaller. Okay, I knew these values because I have it from my tutorial, but if you do not know these values and you are setting your case for the first time, I recommend you to do it iteratively. This means that you will use some values, you will go to TCFD manager, mesh the case, check the case or geometry visually, and then if it's not enough, refine it more. Because you want for your geometry to be as same as STL files, and if you have some discrepancies between STLs and how the mesh look like, then the mesh is coarse and you need to refine the levels more. Then, besides minimum and refinement levels, there are boundary layers, but I'm not going to change them here. And then there is number of mixing planes. And the interface between impeller and volute, I will use here more mixing planes, not 0 as between pipe and impeller, but here I will use 5. This is everything to patches table. I press apply and scroll down. Again, I'm not going to use gap refinement and cylindrical mesh. I'm going to show background mesh size and use the values I used in inlet pipe. So I use 10, 10, 10. But this was enough for inlet pipe. But impeller is much more complex, and it doesn't only need to be refined close walls and blades, but also in mesh volume. So I'm looking for much finer mesh between blades because there is not enough cells between blades. So I'm going to decrease it, for example, to 666. And now it is a bit better in the volume, but still, if I check the distance between blade and the impeller outlet, there is only one cell. And that's why I use even smaller background mesh size. And now it's finer, and with combination with the refinement levels, I should get mesh fine enough in small areas to get the proper mesh. This was background mesh. I can hide the wireframe, and the last thing I need to specify here is internal point. So I show internal point, I zoom out to locate it, I see it's again in 0, 0, 0, and now to get it into my impeller, I need to just get it somewhere else. Now I need to rotate the geometry to see if it's placed correctly. It looks like it's inside and it's between blades, so it is in mesh volume. So this is okay. I need to be sure that internal point doesn't fall between blades, because here I will not have mesh in a thickness of my blade, and if I selected it here, then the impeller would be again meshed from the outside, and I don't want that. I want the inside part where the water flows. So I can hide it, press apply, and I'm done with component 2. But I'm going to check the component graph, and this time I have inlet specify with inlet pipe, the first component ready, and also second component ready. In this case, now the interface between inlet pipe and impeller changed. Now the line is thick because the interfaces are connected from both sides, and now it's set correctly. And again, outlet interface is only dashed because interface is connected only from side of impeller and needs to be connected from component 3 for the connection to be completed. Also, I see that impeller is rotating component. To finish the mesh setup, I have to go to component 3. In component 3, I again specify STL directory, press OK. STLs are loaded into patches table. Then I rename component name to volute. Reference frame stays static because volute is not rotating. Volute is not periodic segments, so number of periodic segments stays 1. And now I specify the patches for volute. The first is volute RSE connection, which is wall. Then there is volute inlet, and that's inlet interface connecting impeller and volute. Inlet interface, and here I right click and connect it to impeller. Then there is a volute outlet, and its overall outlet from my computational area, so I choose outlet. And the last is volute wall, which is wall. Here it's static, so I don't need to change it. Minimum and refinement levels stay the same because the geometry is simple and similar to pipe, or at least with size. That's why I also use the same background mesh size as in pipe, 10, 10, 10. It looks reasonable for a tutorial. If I want, because I want tutorial to compute quick, it needs to give reasonable results, but it needs also to be quick. If I wanted to compute this case as a benchmark, I would need to use much finer mesh. Then I specify internal point. I move it to volute, but I see that it's outside. I need to also move it in this direction, and now when I rotate the geometry, I see this time it's inside of my volute. So it's also okay. I can hide it, press apply, and this is everything to my component setup. So I can close it. I check component graph, and this time everything has complete arrows, no dashed lines. Inlet and outlet are connected to my components. I see that inlet pipe is static, impeller is rotating, volute is static, and they are all connected by interfaces. So this is how it should look like. It's correct. I can close it. I don't want to change anything in advanced SnappyHex mesh options. They are good, or defaults are reasonable, and I can continue to simulation. The first subsection in section simulation is solver. In solver tab, I first set the number of processors I want to compute on, and usually it's the number of processors my computer have or computer cluster I want to compute on. In my case, my computer has 6 processors. Then very advanced option is to change the solver into different solver than default, but usually it doesn't happen. Then you have an option to change numerical order from first to second, but as a first option it's good to use first numerical order to improve stability of your case, and if you have a case with good convergence and you have results, then you can try higher numerical order to get more fitting results. Then there is a convergence check. Convergence check checks if the values from calculation doesn't change by a lot in iterations. This means that if the flow rate or efficiency doesn't change over averaging window, which is 100 iterations, over more than 0.1%, then the simulation is considered to be converged and it stops. So even if I set a large number of iterations, but the convergence check condition is fulfilled, then the simulation starts prematurely and is considered to be converged. For more details, you can hover over the convergence tolerance and read the hint about these windows. This is everything to solver, and I can continue to controls. In controls, I can set relaxation factors, bounding limits, absolute and relative tolerances. These are advanced options, and for good cases you do not need to change them, but if your case doesn't want to converge very well, then you might consider changing these values, but to do that you need to know what they mean. I'm not going to change them, so I can continue. Then there is scripting, which allows us to add some functionality which are currently not possible to do in a user interface by loading some script and different times of stage of case creation, either after writing case, after meshing, or after computation, or between steady state and transient simulation, or completely in the end. But usually this is not important, it's only for very specific cases, so I don't need to change anything here. I close simulation and I continue to boundary conditions. First, there are inlet boundary conditions. Here I can set how I want to specify turbulent quantities at the inlet. I have multiple options and I leave it at default in this case. Then I can specify number of inlet boundary conditions. If I have multiple inlets, I can increase number of inlet boundary conditions, and I can use different boundary conditions for different inlet. Then I can assign the boundary condition to all inlets or only some of them if there is more of them, and there is a boundary type. In my case, I will be using volumetric flow rate. And then I set a boundary condition for every one of my 3 points. In this case, I will be setting volumetric flow rate in liters per second, and I will set 176 liters per second for first point, 156 for second, and 136 for the last point. Then I can specify turbulent quantities, but I don't need to change them in this case. I close inlet boundary conditions and continue to outlet boundary conditions. Here again, if I have multiple outlets, I can choose multiple outlet boundary conditions, assign them evenly for all patches or for every outlet separately, and then I have different boundary types for outlet. Default is fixed pressure, but in this case I will use fixed mean pressure. And I can leave 0 pressure, 0 pascals here because this is incompressible simulation and I don't need to specify the pressure. Besides reference pressure, I specified in fluid properties. These were outlet boundary conditions. Then there are interface conditions, but these are only for fun pressure jumps and they do not make any sense for pumps, so I skip them. And then initial boundary conditions, inertial conditions. I can use inlet turbulent values as initial. Then I can choose if I want to set manual initial boundary conditions or if I want them to be mapped. If I select mapped, I can select some case I have already computed with very similar to close to identical mesh, and then I can map these results as initial conditions for my case. But for it I need to have some results already. So I'm going to use manual. I leave pressure at 0 because also my outlet pressure is 0, and then I set velocity, and I set velocity in a direction of a flow, so in this case in plus z, like this. But incompressible cases are very stable, and usually any initial conditions should lead to a good solution. This is everything to boundary conditions, and I can continue to post-processing. First subsection in post-processing is report. In report, I can decide which sections of report I want to include into my report. Then I can change report quantities like flow rate or velocity, or change different units for some variables. Then I'm able to decide which stream path I want to use if I have more complex geometry with leakages and additional secondary flows. Then I can add some additional data into my report. If I have results in external file and I want to compare them with my current simulation, I can add some file in here and says which columns should be used in which graph. If I do this correctly, then some additional plots with external data will be added to report, and I can immediately compare the results from my current computation with previous results. Then there is efficiency probe. In efficiency probe, I can specify inlet, outlet and torque patches from which I want to compute efficiency. I can also select multiple efficiency probes if I want to For example, not compute efficiency between inlet and outlet, but only for impeller, and in that case, as inlet patch, I select impeller inlet and outlet patch impeller outlet. In this case, I will get efficiency only for impeller. Then there are forces, when I can get values of forces on walls, and in external aerodynamics cases, this allows me to get lift and drag coefficients. This is everything to report, and I go to Turbomachinery. Here there is blade-to-blade view and meridional average, the things I can add to report, and more of them or how they work is explained in TCFD post-processing video tutorial. Then there are samples where I can add some sample probes. For example, if I want to know the pressure on the blades, I can specify it like this, and I get these results in a specific file. Then I can specify any probe in any location in my computational mesh or computational area, and I will get the results from that point. This is everything to samples, and I can check mist, which is last part, and here I have an option to write the results and mesh into CGNS format, or write surface quantities and prepare them for structural analysis. This is everything to TCFD setup. I can press apply, save the changes, click on check setup. My setup is okay, and now I can continue to TCFD manager. Right now I'm not able to do it, so I need to click on PAM TCFD or settings, and now I'm able to use TCFD manager. I click on TCFD manager, press apply. Some additional windows appear where in top part I will have a report when it will be generated, and in lower parts I have quantity monitor and residuals. To write the case, I click on write case. Now I'm waiting until the case is written. It's written, and I can click on run all to get computation running. If I'm running the case for the first time, I'm usually trying only mesh all, checking the mesh visually by clicking on show and visualizing the mesh instead of components. And if I'm confident that mesh looks okay, then I'm continuing to computation. But this is a tutorial. I know that my tutorial works, so I can go directly to run all and compute everything at once. Now meshing starts, and when meshing ends, there will be computation, and after computation, report generation. Now I need to wait. After successful meshing, I'm able to click on render view, hide components, and when I have visible eye next to mesh, I'm able to show mesh. Larger components need longer to be loaded, but after some time they appear. And like this, I can check the quality of my mesh. I can also show only one of the components or everything at once by clicking on show next to merge mesh. After meshing is done, computation starts, and it shows approximate time where should computation end. And during simulation I can also watch residuals and quantity monitors. If I close render view to make these windows larger, and also if I close report, they are large enough, I see that the first computed point already converged or finished after 500 iterations, and now mass flow rate changed for the second point. Also, residuals are dropping. If I want to change what I see in quantity monitor, I click on quantity monitor, then I click on quantity monitor in pipeline browser and scroll lower. And I can choose from all these variables. For example, instead of mass flow rate, I want to see efficiency. So I click on efficiency and average efficiency. And like this, I can watch any quantity or variable from computation. Then, if I want to return to render view and see geometry, I can also split the window again, or I can open new layout, click on render view because geometry is shown in render view, or I can click directly on mesh and render view appears. It takes some time for mesh to be loaded, but I'm able to see mesh in one layout, quantities in second during the computation, and I can also check report in third layout. Now I only need to wait until the computation is done to see the report. Computation is now done, the report is generated, and in report window, report appears. I can scroll down to see the results from the report, or I can save the report in PDF, or if I want to see results in geometry, I can go to render view, hide the mesh, and click on show results. Results are loaded into user interface. I need to wait until they are loaded, and then I'm able to watch the results in geometry. If I want to see results in different times, I can move the time with selecting different time, and if I want to change a different variable, then I can select it from these list of options. And this is everything to this tutorial. Thank you for your attention.